All right. Yeah. We're going to talk a little bit about two different use cases that we've used Model on Impact and Modelica to do at EPRI, which is the company that Garrett and I, my colleague, work at. So just a little bit of background about EPRI in general. EPRI is a nonprofit research institute. It stands for the Electric Power Research Institute. We have we're US based, but we have a expanding global presence now. And we work a lot, especially on these optimization and dynamic modeling projects. We work a lot with international companies. So, we're objective and independent, and that's why we get a lot of companies coming to us to help them with these type of modeling questions, and hopefully as many answers as we can provide through the model. So within EPRI is the Low Carbon Resources Initiative. So that was a subgroup initiative that was created at EPRI with a bunch of different technical subcommittees. And so one of those is electrolytic processes, which me and Garrett support pretty, most of our time is supporting that group, because these models that we work on are typically focused on green hydrogen or some type of hydrogen derivative production. So we interface a lot with all of these different TSCs within the Low Carbon Resources Initiative. And because that initiative is focused again on low carbon, that's why we are starting to look more and more into these types of optimization and dynamic models to understand the balance of plant components and considerations that are needed for these types of systems when people come to us in terms of just understanding the overall configuration, and then going a step further and having some really well-informed inputs from all of the EPRI research that we've collected and then used to inform the models, and then going one step even further into kind of what Garrett's doing, which is the dynamic modeling of specific components that we can inform with different EPRI research. So one of the case studies here that I wanted to quickly go through and give Garrett some more time to highlight his work is the optimization of the cost of hydrogen target. So this is a screenshot of the Model on Impact interface of that configuration. Some background on just the target itself. Typically when we do these optimizations, we optimize for total cost of ownership within Model on Impact. But we had a member come to us that they're interested in levelized cost of hydrogen. And they wanted to know if we could use that as a target to optimize the model to minimize that. And so, going back and forth a little bit, there's a lot of financial parameters that are included in LCOH that really are just, they're things that you can adjust, but they're not really something that you'd want to try to optimize, they're mostly financial parameters. So we started simplifying that more and more to exactly what might be of interest. So that ended up being, just looking at total cost and total hydrogen production, trying to optimize a model for that. And so this was definitely an iterative process. We started looking first with the electrolyzer itself, because I think typically when people look at LCOH, they're thinking, all right, you have an electrolyzer, you have some type of hydrogen production and some type of cost associated with that electrolyzer, and that's your along with all your other debt equity ratio and things like that, you have an LCOH. But when we went to optimize for that, if you're not considering where your energy's coming from, essentially the model will try to just optimize to build out as much energy as it can, like solar or wind, or utilize a very large grid interconnection to maximize the capacity factor of that electrolyzer. So that is definitely true if you have a very low cost like renewables or some low cost grid connection there. So what we went to instead was instead of just considering the capex of the electrolyzer and the hydrogen production, we took the system costs and then in consideration with also the hydrogen produced. So you're trying to optimize on pretty much a simplified system cost divided by total hydrogen production. And so just wanted to do a quick comparison here because this is definitely ongoing work that we're still going through right now. But this was the TCO optimization. So this is kind of more what you would expect when we go to do these yearly optimizations. Again, the electrolyzer is operating flexibly and kind of following the sun here. And there's a lot of ramping up and down of the electrolyzer to meet its target and have the lowest total cost of ownership. But when we went to optimize with that system cost of hydrogen, which is kind of like an instantaneous cost of hydrogen looking throughout the year, we ended up seeing that it's almost like there's a synthetic constraint, the operational constraint that's being made. Because essentially you would think that like what your optimization results for TCO would be the same as your optimization for cost of hydrogen. It should, you would want the cost to be the lowest for each, but it actually is essentially making it to where it's not running base load, but it's running at some load range throughout the year and doesn't ramp up and down as flexibly as we might expect. So this is, again, is something that we're currently working on to try to understand how we might be able to capture that instantaneous cost of hydrogen and see if it does end up with results that would be similar to TCO. But ultimately, we still have an LCOH calculator within LCRI that we use, but it's just separate from this. And this effort was to try to incorporate that into the model itself. And so we'll keep working on that. I think maybe a moving average might be the next step, but might be a little difficult to include in the optimization itself. So all that is kind of some of the optimization work that we've done on the overall system. And I'll hand it over to Garrett, who's going to talk about kind of the more component level analysis that we've been working on.
Thank you, Nick. All right. So as we were starting to construct some of these models for our members, we started to get asked questions comparing specific electrolyzer technologies. So just, depending on your use case, which systems that are offered by vendors today are going to provide a greater advantage for your project's bottom line. So we started by comparing two very widely available systems today. PEM, which is proton exchange membrane, for those not familiar, and Alkaline, which is a longer standing, more mature technology. And so as we were building these models, we realized that there wasn't a great way to compare these two technologies in the pre-built libraries in Modelicon that we were using. We needed to add a couple extra functions, and the members wanted to know this information yesterday. So suddenly we found ourselves becoming Modelica developers and get to be in front of you guys here today as a result. So the electrolyzer module had the ability to input custom efficiencies, sizing, and all of that sort of thing. But we needed to include factors such as the ramp rate of the systems as a whole and the minimum load criterion, or the smallest amount of power that you could feed your system while safely producing hydrogen, safety being the key word there. So we took simulated renewable profiles at 5-minute data increments, and we plugged them into Modelon, and we started trying to build out this added functionality. So this is a quick snapshot for those who have not worked within Modelon. This is what the electrolyzer window looks like. And then we just added a couple little functions there that allow us to begin to compare some of these key characteristics of electrolyzer systems. So first thing we needed to do was thankfully a feature that Modelon had already included. And we needed to go from a constant efficiency to a load factor based efficiency curve. Electrolyzers do not operate at a constant efficiency throughout. So believe it or not, actually, as you increase your load to your electrolyzer, your efficiency, if you're looking at efficiency as, kilowatt hours per kilogram of hydrogen produced, actually decreases, because your balance of plant components, your chillers, your compressors, any separators you may have, they're working harder. And at some point, you do surpass that kind of optimum point for hydrogen production. So we included this this kind of dummy function to just begin to account for that. Please keep in mind that a electrolyzer's efficiency curve is not perfectly linear. Our colleagues back home would be very mad at me if I tried to suggest otherwise. But this kind of just served to begin to demonstrate some of that characteristic in operation. So next we needed to look at that minimum load criterion, because that's kind of one of our first big differentiating factors when we're comparing these different technologies. Some systems are able to ramp up at lower load percentages than others, which is a really important thing to keep in mind, especially if you're trying to pair these systems with something like a solar profile to make green hydrogen, which is the name of the game here. So the newer PEM system, or proton exchange membrane systems, are able to turn on and start producing hydrogen safely at a lower load percentage than the older alkaline systems are. So that does offer some advantage that we'll see a little bit later on when we're looking at these renewable profiles. But you can see, just that kind of difference in where you're comparing to when you're not accounting for that already. That amount of time right there, you're not producing hydrogen. Or if you're looking at alkaline, you're not producing hydrogen. So very important considerations if you are trying to create your optimization studies in a way, if you're given like a specific target for production a year, like many projects are, accounting for these differences in your system when you're in early project planning phases is going to save you a lot of time and headache later on. So next, we added the ramp rate, which is just how quickly your system can actually turn on after you've introduced a load to it. And PEM, once again, is able to do things a little bit quicker than alkaline. It's a newer technology. And so it can ramp up a lot faster. And you'll see the effects of that when you're comparing even just from the ramp rate alone. So you've taken a hit here from your efficiency curve. And then now, you're looking at your minimum load criterion and your ramp rate, and you're seeing all of these places where you're starting to take hits on your hydrogen production. And without the ability to compare these factors, it's really difficult to know how some of these might impact your project. And this is just with a constant, nice, clean input signal, which is not what you get in the real world. You get something that looks like this. And that is just one day of typical solar in the region that this project was done in. And if you brought your binoculars, you might be able to see the PEM and alkaline curves trying to keep up with that solar profile in there. But really, I'm just having this on the screen to show you the intermittent nature is very difficult. And anyone who's worked with a mechanical system or electrochemical system in the field knows your systems do not like to operate this way. So PEM being, you have your material science is doing the heavy lifting in your PEM systems. You have this very complex membrane that's able to do some of that work that your mechanical systems that take longer to turn on can't quite do in these situations. That, of course, comes at a cost. So all of this to say, we are not trying to put graphs like this up here and tell you that one technology is better than the other. You have so many factors that go into your project planning. You have your system cost requirements. Are you operating base load? Are you trying to capture every possible electron? Does it make financial sense to even try to do that? And we're not trying to make any of those kinds of statements up here today. We're just showing the importance of being able to model some of these factors and the value of having a tool like Modelica, where someone like us who have fairly limited software or any kind of coding development experience can still come in and begin to put real numbers to some of these hypothetical questions for our members.